Hello there. Today we're going to talk about power and efficiency. We're still in chapter 14, kinetics of particle, work and energy. So, in your engineering life, there could be scenario that you have to decide what kind of motor you want to buy to do certain amount of work. Yeah, you don't want to. If you design a car, you don't want to put a small car engine to a truck because it will not serve the purpose of the truck to do heavy work. And another scenario could be what horsepower of pump you need to buy to supply certain amount of water per second. So to make this kind of decision, we need to know about power and efficiency. So today's learning objective is define power and efficiency generated by an engine or a machine. As an example, see in the left image, the man is trying to open the pickle jar. So how much power you need to open a jar? The more power you have, the more power you can supply from your hand to the lid, the easier it will be to open. This is one example, and the one on the right image, you see there's a rescue chopper, and if you are asked to design a motor that will pull the man up to the chopper, so you need to think, okay, how fast I'm gonna pull him. Is it 1 meter per 30 second? And then what would be the acceleration, and what is the efficiency of my motor that I'm buying, because the power you're putting into the machine, it is not always 100% efficiency. So you have to also consider that and then make your decision. So let's move on and see how can we define power and efficiency. So let's first talk about power. POWER. So if the power generated by a machine or engine that performs a certain amount of work can be defined as P power, which is du and over dt. So du, u is the work, u is the work, and du is the small amount of work, and dt is the small amount of time. So what this du over dt tells you, that the small du amount of work is done by within the small amount of time dt. So from this equation, we also see if this du goes high with the same amount of dt, so the power goes higher. So what it means, the more work you can do in a given amount of time, the more power you have. So the more amount of work you can done within a given amount of time, the more power available. Simple. So let's develop the equation a little bit further. From our previous class, we know that the du, we derived that it can be represented as the dot product of force and displacement, dr. So if we plug that value back to this equation, we have P equals to F vector dot product with dr over dt. So since this dt is a scalar product, so I'm gonna take this with dr. I'm gonna keep the force on the other side of the dot product. so dr over dt. So since r is displacement, and if we take derivative with respect to time, it becomes velocity. So we can write power is a dot product between force and velocity v. So since it is a dot product, we can also say, so since that the power is a scalar, it's not a vector, so it's a scalar quantity that doesn't have a direction. Scalar quantity. So we can represent the power as a dot product of force and velocity. So this would be the velocity that caused by the force. So what is the unit of power? There's two unit. One in SI unit, International System of Unit, is watt, which is represented by W, watt. And we can also have our FPS, foot pound second system. Our unit would be horsepower, HP, horsepower. So what is the relationship between the watt and horsepower? It is defined as 1 horsepower equals to 746. 746 watt. So this is the conversion between horsepower into watt. So let's move to a new slide to talk about efficiency. So efficiency we can represent efficiency by epsilon. So efficiency is the ratio of power output over power input. So the power you provide and then the power you get is the ratio between that, and it is called mechanical efficiency. If the power input and the power output time is the same, so if the power output time and the power input time is the same, meaning we're providing the power at a certain amount of time and we're getting the power out at the same amount of time, then efficiency can also be written as energy output over the energy that we provided, so energy input. So one thing to observe here is that if I provide power of 10 horsepower, right, or a certain amount of energy, there is always loss. For example, in our car engine, we provide fuel, and burning the fuel, the car moves forward, but there's also heat loss. Our engine gets heated up, and then our radiator cools it down, so there is loss. So we cannot use the 100% energy that the fuel has into our car to drive forward. So the output that we make the use of the fuel energy is always less because of the loss, and there is always a friction effect of all the moving parts of the engine and the whole body, and we have to overcome the friction. So due to all of this scenario, the energy output is always or the power output is always less than power input, and the energy output is always less than energy input. So what tells us that the efficiency can only be maximum 1, and which is not possible, so it will be less than 1. So efficiency is always less than 1. So we have defined power and efficiency today, and we're gonna later we're gonna solve some problem using this concept, so it'll be more clear. So till then, thank you. See you in next video.